Let's see. That's in the slot.
Yep. A whole wall.
I was thinking about sitting up there.
I did it.
Wow.
It works.
I have no such qualms. I have no problem placing myself as the most important person.
Oh, this is probably for a flip classroom. That's what this is.
Yeah, that's exactly.
Exactly. Yeah. Very nice. Yeah, I do have some fails.
I actually just helped her. Yeah.
Thanks a lot.
I'm just thinking I tried to do some. I could see where it was.
So I have some things to prepare to do here. But oh, I see. Yeah. Flipped around. Why don't you guys take a copy of this? That's the quiz. That's actually the first page is the last page is. Yeah. You got to go to the.
Oh.
Yeah, take two of them. Yeah,
So
that's
one
it. Yeah. Sorry, it didn't collate. So what I thought we would do is there's three things I'd like to do, but of course you can ask any question you want. First thing I thought we would do is go through this multiple choice quiz in great detail, and we can expand on it a little bit. We'll use each problem to expand on some idea. And then I thought we would go over the tornado problem in great detail. Even if you got it, that's okay. I'm sure there's some things we can discuss in the problem that are not obvious. And the last thing I would like to do is go over one of the practice sets that I sent out on drag, this particular one. That can take quite a while for us to go over all this material. So we'll do the best we can. If people want to stay till 5 o'clock, we could because we're late. So maybe we could go till 5 o'clock if you want. It took us 15 minutes just to get here. Well, I'm noticing that these blackboards and the whiteboard in the back are all dirty. Nobody's cleaned them. Anyway, nice clean. Okay, so let's start with, yes, I need one too. Anybody have some? Okay. Unfortunately, did everybody get the front and the back? The first, okay. Somehow the machine couldn't collate them. Okay. So I think what we'll do is, by the way, most of you did pretty well on these. Most of you did very well, actually, because these are pretty tricky, so that was very good. Well, let's just start with the first one. First one says, in a fluid at rest in a gravitational field, let's just draw a picture. So we have a cup of water here. Here's the water. Gravitational field is, gravitational field is going this way. Here's the ground. So it's going that way. Okay, so in a fluid at rest in a gravitational field, we have some object in here. Let's just say we have an object, sphere. Here's the sphere. Okay. In this situation, you have a fluid static situation, fluid at rest. 3 possibilities. A pressure is the only stress in the fluid. That's obviously the correct answer, right? Well, some people did not get that one. Let's go back. Let's look at the second one. At a point, it says the pressure is not isotropic. At a point. Well, at a point in a fluid at rest, the pressure is isotropic. What do we mean by pressure being isotropic? Can somebody tell me what that actually means? If the pressure is isotropic at a point, what does that mean? Physically, what does it mean? wants to tell me. Right, right. So what it means is if I'm sitting at this point and I draw a dotted line indicating a surface upon which the fluid is acting, then on this particular dotted line, the pressure is going to be acting at this point, sorry. At this point, the fluid will be acting normal to that surface, right? Now, if I have the same point here, here's the same point. Same exact point, right? I haven't changed the point. But now I'm going to draw another dotted line representing another surface. On that surface, pressure acts downward on the surface, but it has the same exact magnitude as it did when the surface was acting this way, right? Same exact. The magnitude of this vector is the same as the magnitude of that vector. It doesn't matter what position this surface is. It doesn't matter. The orientation of the surface doesn't matter.
For the magnitude.
For the magnitude, right? Only the direction, right? So in other words, isotropic means the magnitude is independent of direction. In this case, the magnitude is independent of direction. So essentially, that's what we're talking about. Isotropic means, in this case, the pressure magnitude is independent of direction. Okay, so the answer. Oh yeah.
He's recording.
Okay, so let's see. B says at a point the pressure is not isotropic. That is obviously wrong. The pressure is always going to be isotropic, even if the fluid is not at rest, actually. Okay, let's go to C. Shear stresses can exist. Is that false or is that true? False. In a fluid at rest, there cannot be any shear stresses, right? That can't possibly be correct. The only stress in the fluid is pressure, and that's the end of the story. D. Pressure forces act in the same direction as gravity. Some people answered that. I don't want to embarrass anyone, but anyway. Some people answered C. Is that correct? Here's gravity acting this way, and this glass of water is resting on the surface here. So the question is, if I'm sitting at that point on the sphere, which is submerged in water, at that point, in which direction does the pressure act? It acts perpendicular to. It acts in a direction opposite to the unit normal, right? The pressure vector, if you want to call it that, is magnitude of the pressure times n hat. And what is wrong with this equation? Negative is correct. Pressure, unit normal at that point is acting upward. The pressure P is acting perpendicular to the surface. That arrow is not going in the direction of this arrow. The pressure doesn't know anything about gravity. Nothing whatsoever. Nothing. Pressure is not influenced in any way whatsoever by gravity. Okay, well, most of you got that right. So what I'm doing for the people who came in late, I'm reviewing the quiz in detail. So the answer to number 1 is A. Pressure is the only stress in the fluid. All the other three, B, C, and D, are false. Okay. Anybody have any questions about that? We should discuss it if you're confused. But anyway. Okay, number 2. For potential flow past a cylinder. Potential flow past a cylinder. Assuming a uniform incident flow, what does that mean? So let's draw a picture of that. Oops. Oh, there it is. Right over. Oh, there it is. Okay, let's get rid of this picture. So we've got potential flow over a cylinder. There's the cylinder. It says uniform incident flow. What does that mean? No, it says right here, assuming uniform incident flow. What does that mean?
Straight velocity.
Yeah, where the incoming flow looks like that, uniform. Does not depend on the y coordinate, right? Okay, so that's what we've got. We have potential flow, potential flow. What is a potential flow, by the way? Can somebody tell me what is a potential flow? These questions are good because they give us a chance to get into some depth of these concepts. Because as you recall, there's going to be 40 multiple choice questions on the exam worth 40% of the exam. So the more time we spend on these concept questions, the better. What is a potential flow? We've spent like 3 weeks on it. You can't tell me what it is. How can you not know what potential flow is? Well, yes, you badly.
Flow that's both gravitational and compressible.
Yes, absolutely. Or in other words, it has a velocity potential, right? That's why we call it a potential flow, because it does have a velocity potential. But it's even more than that. It's also incompressible, as you said. Normally, not always, but normally they're two-dimensional, but you can have them in 3 dimensions. Oh, that brings, before we go finish this question, that brings me to another point. If you have a flow that has no vorticity, then it has a velocity potential, correct? So the next question would be, can you have a 3-dimensional flow without vorticity that has a velocity potential, or does it have to be 2-dimensional? So the question is, suppose you have a 3-dimensional flow that does not have vorticity. Can that flow have a velocity potential? Or does it have to be 2-dimensional in order for it to have a velocity potential if it has no vorticity? Yeah, and the answer is that it's not a problem for the velocity potential. Right? Because the velocity field, if you have a potential, is the gradient of the velocity potential, correct? And this is a 3-dimensional operation. It's perfectly okay. So you can have a velocity potential in 3 dimensions. Next question. What about a stream function? Can you have a stream function in 3 dimensions? Oh, let me back up a second. Can you have a streamline in 3 dimensions? Streamline. I didn't say stream function. You say no, somebody says yes. Anybody say yes?
Yes.
Yes, you can have streamlines in 3 dimensions. Why not? I mean, any line for which the velocity is tangent is a streamline. It doesn't matter whether it's 3-dimensional or not. So, yeah.
It's a streamline, right? The line usually has 2-dimensional thing, so it doesn't make sense to say. I mean, I don't know.
Well, let's draw it. So here's 3 dimensions, right? So assuming this is a steady flow, then you know that particle paths are the same as streamlines, right? So why can't we have any old line in 3 dimensions? A particle can travel in any way it pleases in 3 dimensions, right? And if it happens to be a steady flow, then we know the particle paths are the same as streamlines. Therefore, we can certainly have streamlines in 3 dimensions, right? So my next question is it possible to have a stream function in 3 dimensions? That's a tricky question. What is a stream function? A stream function is a function such that u is the psi in y and v is minus the psi in x. But can we have a stream function in 3 dimensions?
Isn't that also, if they do it in 3 dimensions, dimension, isn't there also a W?
Well, that's the question. That is the question. Is there a W?
Yeah.
The answer is, in general, there is no such thing as a stream function in 3 dimensions for a general 3-dimensional flow. No. There are some rare exceptions, but if you read what we said in class, only flows which have certain symmetries in 3 dimensions. For those flows, we might have a stream function. You said something interesting. Let's work it out. Du dx plus d dy plus w dz is 0. What does that equation represent?
Gradient of velocity.
The gradient of velocity?
No, dot, sorry. It's incompressible.
Yes.
Yes.
This equation is the same. This equation is the same as divergence of v is 0, right? It's the same thing, right? Okay, now we're gonna address your question. You said, how come we can't have a stream function in 3 dimensions? Okay, great. Let's get rid of that for the time being, right? Just get rid of that. If I pop this in here and I pop that in over here, it satisfies the equation, right? Right? d by dx of this is going to give us the second derivative of this with respect to x and y, right?
Yeah.
Pop this in here, you're going to get the second derivative of this with respect to x and y. With a minus sign, therefore it's going to cancel, right? What am I going to do with w?
You can't get rid of it.
You can't get rid of it. Right. Therefore, the conclusion is that in general, you cannot have a stream function in 3 dimensions. Okay? Okay, well, let's go back to the problem. Problem number 2. For potential flow past the cylinder, potential flow again is, Natalie said it, it's a flow that has a velocity potential right there, and it's also a flow that has divergence of v is 0, both, right? So we've got 1, we've got 2. If we have these 2 conditions in 2 dimensions anyway, then we've got a potential flow. Okay. For potential flow past the cylinder, A, there can be drag. Is that true or false? It is false. There can never, ever, ever in a million years be drag on a potential flow. Right? There's no way. Because there's no viscosity, basically, right? Can't have drag. Number 2, part B. There can be lift if there is no circulation. That is false. You have to have circulation to have lift. C. There can be, let's go to the third one. There are 3 stagnation points. In general, no, there aren't. You're only going to have 2. You're only going to have 2 stagnation points, right? Generally, right? I mean, you're going to have one over here and one over there, right? That's it. Now, if there is circulation, these stagnation points are going to move around, but you're never going to get 3 of them. You'll never get 3 under any. There's no condition under which you get 3. You might get 1 actually, but you can never get 3. So let's see. So the correct answer to part 2 is there can be lift if there is circulation, right? Because if there is circulation, then these stagnation points move down here, and then we will get lift, right? As you recall. Okay, so the answer to part 2 is C. There can be lift if there is circulation. By the way, what is the equation for circulation? How would I calculate the circulation for any flow? What is the equation? I should say on the final exam, all the equations you need will be on it. It'll either be right on the problem or it'll be in the back. You don't have to memorize any complicated equations, so don't worry about that. Okay, but anyway, give me the equation for circulation. What is it? It's it? Yes. Circulation is V dotted with dl, and you integrate that around a closed curve. Around a closed curve. Right? So if we took a closed curve around this cylinder, and we calculated that line integral, we would get a number. Right? And okay, let's go further with problem number 2. Let's keep going. So suppose I got the flow around the cylinder, and I used a dipole plus a uniform stream to get it, right? Remember, we had a dipole plus a uniform stream, we get this, right? Okay, in that case, will I ever find circulation around this thing? No. It doesn't matter what curve I take to do that calculation, I'm always going to get 0. So what can I do to this thing to get circulation? What am I going to do in order to get lift? Well, right now I've got dipole plus uniform stream. In order to get lift, I have to add something else. What is the something? Yes, potential vortex, correct. If I add a potential vortex to it, I'm going to get a non-zero circulation. Right? Okay. Before we go on, let's continue. What is the relationship between the lift and the circulation? Lift, L. What is the equation for lift? Right. Rho times the velocity, the incident velocity times circulation is going to be the lift on for any potential flow. Okay. I think we're done with number 2. Number 3. I'm surprised that some people didn't get it right. Let's erase all this. Any questions on number 2? I think we beat that one to death. Okay. So I got that one. Let's do a substantial derivative. The substantial derivative of a scalar such as temperature. So here we have the substantial derivative of t with respect to time. Capital D, D operating on t divided by capital D operating on time, where t is temperature. Okay, signifies the time rate of change at a fixed point in space. Is that correct? At a fixed point in space. No, that's not correct. We're at a fixed point in space. Here we are, x, y. How would we specify the time rate of change of temperature at a fixed point in space? How would we do it mathematically?
dt with x, y.
We would calculate the partial, right? Now, what exactly is this thing? This thing is going to be the partial plus v with the grad operator operating on t, right? So this thing's got 2 parts to it. Okay, next one. So A is wrong. B signifies a time rate of change following a fluid particle. That is correct. Substantial derivative is this guy, and that, in fact, is the time rate of change following a particle. So basically what it means is, if I know what this guy is, and if this is a particle and it's moving around, then the substantial derivative measures the temperature of a person with a thermometer who's riding the particle. That's what it's measuring. So B is correct. C is the substantial derivative always equals this. Substantial derivative always equals that. Obviously wrong, because this can be non-zero, right? So can't possibly be correct. D, none of the above. Well, okay, that's not true. Okay. Let's see. Number 4. Number 4. Number 4. So we have a flow such that VR is 0. We have V theta equal to some constant times R. That's the flow. Yes, this actually is solid. This actually is solid body rotation. Right. Solid body rotation. We abbreviated SBR. Okay. So the choices are A has vorticity everywhere. Well, let's skip that one. Answer B is compressible. Is compressible. Is this a compressible flow? No. It's incompressible for sure. Solid body rotation, incompressible. Numbers C is. Let's go to D. Does not have a stream function. Is that true? Of course not, because it's incompressible. Therefore, it's got to have a stream function. It's two-dimensional, right? So that can't be right. So the only possibilities are A and C. Let's go to C. C says, is rotational except at the origin R is 0? Okay, well, let's draw a picture of it. Here's the flow. It's basically like in case of a tornado, it's a flow with closed streamlines, and the velocity profile looks something like this. It's linear, right? And here, flow is going this way. So if I'm going down that axis, velocity is high, then it goes to 0, and then it goes negative, right? So part C says, is rotational except at the origin? Well, I don't know. Let's see. Do I have any vorticity at the origin here or not? Brendan says no. Anybody say yes? You say no. Is there any vorticity at the origin?
Yeah.
Yes, of course there's vorticity at the origin. Now, just because the velocity is 0 doesn't mean there's no vorticity. How do we know there's vorticity there? Well, there's two ways to get it. Calculate the vorticity, but also from physical intuition, right? If I draw a fluid cross right there at the origin, that point is going to go that way, right? This point is going to go that way, right? This point is actually going to go that way, and this point is going to go that way. So this cross is going to spin. And in fact, it doesn't matter where you draw the cross. It's going to spin exactly the same rate everywhere.
Was it take the curl and
Yeah.
set it equal to 0? Or if,
Right.
if it equals 0.
Correct. If you calculate the curl, of the velocity, you will get in this case, I think you're going to get 2 times k, something like minus 2 times k or something like that.
And if it's not 0, then it has vorticity. Right.
Yes, but in this case, it has the same vorticity everywhere, even at the center. Right? It doesn't matter where you are; the vorticity is exactly the same.
Is that the same for all?
Only for this flow. So the correct answer to number 4 is A. It has vorticity everywhere. In fact, it has the same vorticity everywhere. Okay, number 5. Maybe we'll have to go a little faster. Slower. Number 5. Well, why don't we do it this way to speed things up? Somebody tell me what the answer is to number 5 and explain why the answer is what it is. If a flow is two-dimensional, so it's let's write this down, two-dimensional, and we have incompressibility, divergence of V is 0, and it has vorticity. Okay, so vorticity is not equal to 0. Okay, what's the answer? Part A, it has a lot. Somebody tell me, what do you think the answer is? B, it must have a stream function, psi. Well, that's very interesting. Why do you say that? What's wrong with A? No, I want Mike to answer this one.
Oh,
Mike, why is A not correct?
I just know it's B. I don't know why it's not. I just know it's B. I don't know why it's not. Yeah.
We're going to have to go to somebody else then. I mean,
Pretty simple.
you're right, but Yeah, right, but how come A is wrong? That's what I'm trying to get at.
You have vorticity, it can't be.
Right, exactly. Since it has vorticity, it cannot have a velocity potential. Right? So that's right.
Like to have velocity potential, you have to have both
Z-
0 for grad and curl. Or
No.
grade dip and curl.
To have a velocity potential, you just have to have zero vorticity.
Okay, 0. That's the
all.
only condition.
That's the only condition. So A is clearly wrong. Let's go to C. It cannot have closed streamlines. What does that mean? Closed streamlines. Somebody tell me.
I don't know. That's why.
You don't know what it means?
Well,
Closed. What does that mean?
it's divergence.
No. Closed streamline just means that whatever is this a closed streamline? No, because it's open, right?
Oh, like an open or closed circuit.
Yeah.
So it's like,
It's
okay.
a closed circuit.
Oh, okay.
That's what a closed streamline means. So that's all it means. Okay, so according to C, this flow cannot have closed streamlines. Is that true? We don't know. I mean, it could have closed streamlines. Maybe it doesn't. Who knows? But can't say it. There's nothing in those three conditions that tell you that this couldn't be the case, right? So obviously C is wrong. Let's go to D. Here's an interesting one. D says del squared phi is 0, where phi is the velocity potential, correct? Can somebody tell me why this cannot be true for this flow?
That equation is true only for vorticity equals 0.
Yes, because that's true. Because otherwise you wouldn't have a velocity potential, right? So that's true. Okay, fine. Got rid of D. What about E? E says that this is 0. Why is that not true? It's incompressible, so maybe it does have a psi. Why is this not true? It's definitely not true, but why? That's the question. Can somebody tell me? Del squared psi equals 0. This flow cannot possibly have that. Why? No one knows. Okay. So let's go back. Del squared phi is 0. Del squared psi is 0. The only way you can have either of these things, it doesn't really matter which one, the only way that either of them can be true, listen to what I'm saying, the only way that this can be true or that can be true, because if this is true, then that's true, right? If this is true, then that's true. If this is true, then that's true. So it doesn't matter which one we're talking about. The only way that either of these things can be true is if, well, you tell me, is if what? Two conditions have to be satisfied in order for either of those two to be true. What are the two conditions?
No vorticity, no incompressibility.
That's right. We have to have incompressibility, and this has to be 0. Both of those have to be true. Otherwise, there's no way that either of these two conditions can be true.
So if the first one's not true, the second one's also not true?
That is true.
If you have vorticity, does that mean you have to have? That means that the flow is broken.
No, okay, yes. Okay, let's go back to, I understand what you're saying.
Because
If the flow has no vorticity, then you do have a phi. Yes. But that doesn't necessarily mean it's going to satisfy del squared phi is 0. It'll be something, but it doesn't necessarily satisfy Laplace's equation.
Okay. So, Professor, if we go back to that definition of psi, and
Right.
if we have U and V for a compressible flow, incompressible flow, then wouldn't that equation satisfy that?
Wouldn't this equation satisfy this?
Yeah, like
No, it wouldn't.
if it's incompressible.
It would not. Remember, where did these two equations come from? They came from a very famous mathematical condition. What was the mathematical condition called? Named after two very famous mathematicians. Cauchy-Riemann conditions, right? Well, the Cauchy-Riemann conditions say the flow is incompressible, so you get a psi, but you must also have irrotationality, both, simultaneously. You cannot go back to your notes. Neither of these can be true unless you have both incompressibility and irrotationality. Right? Okay. Okay, so the answer is, without a doubt whatsoever, the answer to number 5 is it must have a stream function. It's the only possibility. And the only reason we know for sure, how do we know for sure that this flow has a stream function? How do we know for sure that this flow has a stream function for 5? Yes, but that's good. Two-dimensional, right? If we did not specify that it was 2D, then you wouldn't know for sure whether it had a stream function or not. This is very subtle stuff. This is very tricky stuff. Don't take this for granted, right? Problem number 5 is, they're all tricky, but problem number 5 is very tricky. Very tricky. Okay. Expect to see a couple of those on exam. Okay, any problems with number 5? Yeah, yes. Yes, we do. Where are they? Somebody pass, have a lump of those guys? Yeah. Yeah, there we go. Okay, that's good. I think that was a good discussion on number 5. We covered a lot of material there. Any, if you want to stick with number 5, you can do it. But I understand number 5 is very hard.
I was just wondering if there is a like for the solid body flow, if I like that would satisfy that equation. Right?
No, okay, that's a good question. Harshford actually asks a good question. If you have solid body rotation, which is what we talked about in number 4, can somebody please tell me whether that flow would satisfy either of these conditions? Eric, you say no.
Yeah.
Why do you say no?
They have vorticity.
That is correct.
No way.
That is correct.
So even the second one will not be satisfied?
Neither of them will be satisfied for solid body rotation. Neither of them. Solid body rotation is not a potential flow. Not a potential flow. Any other questions on number 5? Well, since you mentioned that, what about a potential vortex? Would a potential vortex have a phi and a psi that satisfied both of these?
Yeah, except at the second, right? Like it doesn't have vorticity.
No, but that's not the question I asked you. I asked you whether a potential vortex would satisfy either of these. I'm not asking you about vorticity. You're answering a different question.
Yes.
Yes, the answer is yes. A potential vortex does satisfy either of those, or both of them. Okay, good. Let's go to number 6. Number 6. Let's see, number 6. Let's write these down. And here's a very important clue. Well, not a clue, but a method. When you see these on the final exam, it's a very good thing to scribble next to it. You know, for example, let's do number 6. Okay, steady. The word steady shows up. It's a steady flow. Well, don't just write the word steady there. It doesn't help you. Say steady means that the partial derivative of everything is 0. That's what it means, right? So you have a mathematical equation, right? So identify the word with the equation. Don't just write down the words. Don't just underline the word. It doesn't help you, right? Okay, then it says irrotational. IRR, irrotational. What is that? What is the mathematical equation for that? Curl is 0, yes. Or we could say the vorticity is equal to 0, which equals the curl of the velocity. Either way. So now you've got an equation there sitting in front of you, right? Next, incompressible. INC.
The div, so dot product
Right.
is
Right. Divergence E is 0. So you notice that these words really don't help you very much. It's this stuff that's going to help. What else? Oh, flow of a perfect fluid. Yes.
So I would assume you said you were going to give us equations, but I would assume on the final exam you're not going to give us like simple equations like that.
Yes, you're going to have to tell
Okay,
that.
okay,
That's
thank
right. You're going to have to know. Yeah. Correct. Okay. Perfect fluid. That's another word, another 2 words. Perfect fluid. Give me some equations. Don't- U is 0, yes. Yes, very good. Okay, now you're in a position to solve the problem. Now you're in good shape. Okay, now you're in good shape. Part A. The Bernoulli, okay, now we're getting into the Bernoulli equation. That brings up another topic. Part A brings up the Bernoulli equation. Let's talk about the Bernoulli equation. Yes, let's summarize the whole thing. Yeah, okay. Bernoulli equation, let's talk about it since that's coming up. Okay. So in this course, we're pretty much devoting all our effort to incompressible fluids. So don't worry about compressible fluids, right? So what are the 2 possibilities here? There are only 2 possibilities. Mu is 0, and mu is not equal to 0, right? That's it. This is a flow chart that you should write down on your test if the Bernoulli equation shows up anywhere. There's only 2 possibilities, right?
Isn't it vorticity equal to 0?
You're getting way ahead. We're coming to that. Okay. Put that in a box. Put that in a box. Let's start out. So the first question you ask yourself is, can I use the Bernoulli equation? Right? So to answer that question, it's like a computer program. Is this true or is that true? Right? Those are only 2 possibilities. Suppose that this, let's actually focus on this first. What does this equation, mu equals 0, mean? What does it mean?
Effects of what?
It means, so you're saying that,
It doesn't have viscosity.
what did you say?
Effects of
Effects of viscosity are 0. Yes, it doesn't, yes. It does not mean the viscosity is 0. No, this is only a shorthand notation for what you're saying, which is much more subtle, much more complicated, right? I'm not going to write down the words effect. I can't do that. It's too. I don't have patience for that. When I say mu is 0, I don't mean that the viscosity of the fluid is 0. Why do I not mean that? Because there's no such fluid in the world except for exotic fluids, right? Super cool fluids or something. So if this question shows up on the exam, you should know the answer. Mu equals 0 does not mean that the fluid has no viscosity. We'll come to this in a minute. It just means that the effects of viscosity are negligibly small. That's all it means. Okay. And what does mu not 0 mean? Just means that the effects of viscosity are not negligible. Yeah, substantial, right? Okay. Suppose that we have this condition. What is the answer as far as Bernoulli goes? No. Cannot use Bernoulli ever. Okay. Now we come to this. And the answer is yes. Yes, we can use the Bernoulli equation. Absolutely. By the way, before we continue, where does the Bernoulli equation come from? Yes, it comes from the Navier-Stokes equation. It's not separate from the Navier-Stokes equations. It's a subset. It's a consequence of those equations. It's not. Okay. So yes, we can. Now, there are 2 branches here. 2. What are the 2 branches? Now, your question. What are the 2 branches?
vorticity equals 0, vorticity
Right, vorticity not equal to 0, and vorticity equal to 0, correct. And this is a very powerful way of figuring these problems out on a test. Drawing this flow chart. Okay, let's go to this one. By the way, by definition, we're assuming divergence is 0. So here we are. We can apply Bernoulli's equation, but what kind of situation do we have here? Yes, can be applied. Between any 2 points in the flow. Sorry for my sloppy handwriting. If the vorticity is 0, you can apply the Bernoulli equation between any 2 points in the flow. Now, what does that imply about the Bernoulli constant? How many Bernoulli constants do we have in this situation? 1. 1 Bernoulli constant. The entire flow is defined by one number. One number, which is the Bernoulli constant. Okay, now we come to this case, which we're going to get to a little later if we have time. This case, what's the story? We can use the Bernoulli equation, right? But under what restrictive conditions? Yes. Only on streamlines, correct. Only on streamlines. Next question. How many Bernoulli constants do we have in this situation? Yes, infinite number. Because if we have an infinite number of streamlines, we have an infinite number of Bernoulli constants. Every single streamline has its own Bernoulli constant. Okay, so now we've got that done. Let's go back to the problem. Number 6. So here's the situation we've got. Here it is. Part A says, the Bernoulli equation cannot be used along streamlines. Let's see. If that's true, then it must be this case. And it looks pretty good. Oh, sorry. No, it doesn't. It cannot be used along. Of course, it can be used along streamlines, right? Because we're talking about this case and that case can be used anywhere, right? We've got vorticity is 0, and we have a perfect fluid. So let's find out. Perfect fluid. Yes, we got a perfect fluid. Therefore, we can use the Bernoulli equation, right? Well, let's see. Vorticity 0. Check. We're going down that way. So this says it can be applied between any 2 points in the flow. Doesn't matter whether the 2 points are on a streamline or not. So part A says the Bernoulli equation cannot be used along streamlines. That cannot possibly be true, right? Because it can be used anywhere in this flow, right? Okay, B. The Bernoulli equation can be used between any 2 points in the flow. That's obviously correct, right? Because it's this case, right? C. A stream function must exist. Oh, a tricky one. It's a tricky one.
It's because it doesn't say it's two-dimensional.
Yes, exactly correct. Yes, exactly. Connor said it exactly right. It says divergence V is 0. It doesn't talk about two-dimensionality, so you don't know for sure whether a stream function exists or not. You know that streamlines exist, but you don't know whether stream functions exist, right? So it's very tricky. It's not simple. Part D. Velocity potential does not exist. A velocity potential does not exist. Why is that wrong? Yes, because of we know it has no vorticity, therefore a velocity potential does exist. It doesn't matter whether it's 3-dimensional or 2-dimensional, right? It's irrelevant. Is everybody getting this idea, this point about the stream function? Okay. Okay, done. Number 7. Let's erase all this. Number 7. Seven. The Reynolds number. Well, let's write down what the Reynolds number is. The Reynolds number is the density times the velocity times some length divided by the viscosity, right? That's by definition, right? Or we could write it rho, we could write it U times L over the kinematic viscosity. It doesn't matter. Either one, right? Because I can divide both top and bottom by the density, right? Get the kinematic viscosity. So same thing. Okay, so here that's the Reynolds number. Let's see. The answer is A, right? It's inertial forces over viscous forces. It is not viscous forces over. You don't see gravity in there. Where do you see gravity? I don't see G anywhere, so it can't possibly be that. Gravitational forces to inertial forces. Again, where's gravity? We don't see them. Elastic forces to pressure forces. Where do you see pressure in here? Right? This one's pretty easy, right? Even if you don't know the answer, even if you don't know the answer to the question, if you write this equation down, you should be able to solve it, right? But the answer is definitely inertia to viscous forces. And let's go a little further. What happens when the Reynolds number, somebody give me an example of a case where the Reynolds number is, I don't know, equal to 10 to the minus 5.
It's not the baseline. It's not where it's like I remember you saying something.
I'm saying almost 0 here.
Oh,
Reynolds number
-5.
almost
Wait,
0.
what was it when
Negative
it's 10 to,
5.
what was it when it's 10 to the 5th?
Oh, that's,
Less than
we're coming to that in a minute.
oh, okay.
Somebody give me a real example of Reynolds number 10 to the minus 5. Several examples. Say it again. Yeah. You could have a pipe flow at very low Reynolds number, but that's not. Okay, let's take pipe flow. Here's a pipe. You said it. Everyone said it. I have a pipe flow. Under what conditions? That's a very good question. I have a pipe flow. Under what conditions would I have a very tiny Reynolds number in a pipe flow? Yeah, it could be right. It could be a pipe with extremely small diameter, like a micro pipe, or yes, or a very very slow velocity, or an extremely large viscosity. Right. In fact, it can even be a flow, as Professor Shapiro pointed out in the film. It could be a flow with any old mu, but if the density is very small, that's another possibility. Like, for example, if you're near outer space, you can be moving at a very high speed, by the way, but if your density is tiny, you can still have a low Reynolds number. Right? So there's many, many, many ways that you can have a small Reynolds number. Many, many ways, right? You literally have 1, 2, 3, 4 numbers, 4 physical quantities there, such that you can have a very low Reynolds number. But give me another obvious example, because pipe flow is not obvious because we can make the pipe anything, right? Any diameter. So give me another example in your everyday life where you have a low Reynolds number flow, nearly 0. Yes.
Blood in like veins.
Yeah, a capillary in your very tiny veins. Yes, that's true. But I want a case that you see in every time you almost in your daily life you see this. You can literally see it. How about ketchup coming from a bottle, slowly flowing from the bottle, right? How about
Well, in the ketchup bottle, the liquidy tomato stuff comes out, and then the ketchup comes out. But
well, I'm just talking about very, very, very slow. How about if you have honey in a jar, you take a little bit of honey, you just have it very slowly drip. How about let's see here. How about toothpaste coming out of a tube, right? Very slow. I don't know if it's going to be 10 to the minus 5, but really small, right? Actually, there's even better examples than this. One of the best examples would be what?
The tar experiment you should have seen.
Tar, yeah, but that's not something you see in your daily life.
Oh, right.
Another thing that you don't see in your daily life, but you know about, would be small bacteria that are incredibly tiny, that are in your body right now that are moving around, those things are at incredibly small Reynolds numbers. Okay. Okay, so the answer is definitely A, inertial forces and viscous forces. No question whatsoever. Oh, just out of curiosity, give me an example where the Reynolds number is 10 to the, 12th power. What? Well, yeah. You can always make the Reynolds number 10 to the 12th if you have the fluid is moving at the speed of light, maybe, or anything like that, right? But I'm talking about just an example that you would see maybe every day, maybe.
There's something with really low viscosity, so like liquid nitrogen or
You don't see how many times do you see liquid nitrogen in your everyday life?
you don't know me, Professor.
Where's your liquid nitrogen?
I don't know.
How about when you're watching television sometimes, and you see a satellite image of a giant hurricane or storm?
Oh, okay.
Those have incredibly large Reynolds numbers. I mean, probably, I don't know what it is, but it's probably close to 10 to the 12. But the size of the storm is like, some of these hurricanes can be 500 miles in size, right? And with high velocities. Of course, you're going to get huge Reynolds numbers. Okay, let's go to number 8. Number 8. Fully developed laminar flow in a pipe. Well, there we go again. Here we go. Fully developed laminar pipe. If you're going to solve this problem, write those words down next to the problem. What does fully developed, what is the equation for that? Well, let's draw a picture of a pipe first. There's no equation for a pipe. There's the pipe. It has a diameter of d. And let's just call this coordinate the x coordinate. What equation do I want to see here? What equation should you write down on your exam paper for those words? Yes! Partial of whatever it is you're talking about with respect to x is 0. That is what fully developed means, right? No dependence on the direction in which the fluid is going. What about laminar? Well, is there an equation for laminar flow? Not really. Just means maybe we should say not turbulent, right? Very, very orderly flow. Very orderly flow. Orderly, maybe orderly would be a good word. Orderly flow. Okay. So let's see. In this case, let's start with B. A logarithmic velocity profile exists. What does that mean? Here's the pipe. Here is X. Here's R. What does the velocity profile mean, right? It means that I'm drawing a line here, meaning every single particle here has a velocity, and it might be anything, right? It's got to be 0 there, and something in between, right? It says, a logarithmic velocity profile exists in laminar pipe flow. Is that true? No. A logarithmic velocity profile exists in a turbulent pipe flow. Yes. Not in a laminar pipe flow. C. The pressure drop will increase in proportion to the square of the flow rate for laminar flow. What does that say? The pressure drop, delta P, increases in proportional to the velocity squared, right? What is the pressure drop in this flow? What is it physically? What am I talking about? Pressure drop. What does that term mean?
Pushing the fluid.
Between 2 points, right?
Yeah.
If I'm over here and I measure the pressure with a manometer, and I'm over here and I measure the pressure with the manometer, the pressure drops from A to B, right? The pressure decreases as you move down. Why does the pressure decrease in a pipe flow?
Is that if it's fully developed?
It doesn't matter whether it's fully developed or not. Why does the pressure drop as I go from A to B, assuming that the flow is going this way? Why? Is it just because I'm telling you that it does? Why does it drop? Not really. What's the physical meaning of this?
going from A to B.
By the way, the word pressure drop is used all the time in engineering, right?
Yes.
People are concerned with the pressure drop in a pipeline. Yes.
Because pressure is strongest at the head of it.
Is it surface time? No.
We discussed this in class. Let's take a chunk of fluid out of here, right? Draw a free body diagram. Here's the chunk of fluid, right? Here it is. There it is. You tell me, it's like a flip class, I guess. You tell me, what kind of forces are acting on this face of the fluid that I just took out of the pipe? Pressure, yes. P1.
And the atmospheric on the other side. So
Well, we don't. Well, it's inside the pipe. There's no atmospheric pressure here. Atmospheric pressure is way over here.
So then
Shear.
What force acts on here?
Another
the opposite.
Another pressure force. But pressure acts perpendicular to the surface. So that must act that way, right?
Well, it has to be smaller because otherwise, if P1 isn't bigger, the fluid doesn't move, right?
Well, why? I mean, you're not that. Why should this pressure be bigger than that pressure?
Because if it's
If
not,
this
then-
pressure.
like if they were equal, it'd just be static, right?
Well, not necessarily.
Oh.
I mean, if the pressure on two sides of a particle are exactly equal, the particle can still be moving. Just means that the net force is zero.
What do we do with constant velocity?
Why does this pressure have to be bigger than that pressure? I know you know the answer. What's going on up here?
Nothing.
Shear. Who said shear? Somebody said shear. Yes. There is pressure, of course, but we don't care about that. There's shear stress. This shear stress always has to be acting in the direction opposite to the direction of flow, right? So it's got to be acting that way. It has to be, right? What's going on there? All the way around the chunk, which is a circular chunk. We've got these shear stresses. So that's the answer, right? In order, if the fluid is flowing, there's a net drag force on the thing. In order to keep this thing moving at some speed, any speed whatsoever, then this pressure's got to be bigger than that pressure to balance the drag, right? So that's the reason. Okay, so let's go back to the problem. B is wrong. A logarithmic profile, that's wrong. And part C says the pressure drop, meaning P2 minus P1. P2 minus P1 is the pressure drop.
But it can't change with respect to X, right?
Right. It's a constant pressure drop. It's a constant. Well, it depends on the distance between the 2 points, right? The further apart you are, the bigger the pressure drop. Right.
Mm-hmm.
The pressure gradient is going to be constant, but the pressure drop is not going to be constant. Okay. The question says the pressure drop depends on the velocity squared. Is that correct or not? We discussed this in class. No, not for a laminar flow. For a laminar flow, it's proportional to the velocity, not to the velocity squared. This would only be true in a turbulent flow. Okay. Part D. The pressure drop will increase in proportion to the cube of the flow rate. The pressure drop will increase in proportion to the cube of the flow rate. That's obviously wrong. There's no way, right? That's not even true for a turbulent flow. Nothing, right? Okay. So the correct answer to 8 is a parabolic profile exists. That's the standard exact solution to the Navier-Stokes equations, the Posai flow. Right? So the answer to 8 is definitely A. No question about that. Okay, let's move on to number 9. Laminar boundary layer of a flat plate. Ooh, okay, this is a tricky one. Laminar flow over a flat plate. Okay. So what you should do on a problem like this is draw a picture. Here's the flat plate. Here is x. Here is u infinity out there. And of course the boundary layer grows somehow. And it has a boundary layer thickness of delta. Now you're ready to go. And it says a lambda boundary layer. Let's do the problem. Let's remind ourselves of what's going on here. The problem refers to the boundary layer thickness. But for a laminar boundary layer, you should remember, and the equation actually probably is going to get a test, that the boundary layer grows like square root of, actually proportional to the, let's see, it's going to be nu t, and t is going to be length of u over L. It's going to be actually L over u. L over u. This is the kinematic viscosity right here. That is the distance downstream. Actually, we'll call that x. Some position x downstream. There it is, right there. And that is the incoming velocity. This equation, you know, you should memorize this equation, right? Well, there's another equation which you probably also should remember, which you know will probably be on the test for sure, which is this one. But this equation is the same as this one. They're the same thing.
Is that 5 or an S?
That's 5. Well, don't memorize this, but it'll be on a test, but you should know what it means, right? What is Reynolds x? Reynolds x is u infinity x over nu. So this equation is the same as this equation. There's no difference between those two. It's just that this equation is a slightly fancier way of writing this one. Right? So let's review it. Delta, what is delta? What is delta? The boundary layer thickness, correct. What is the boundary layer thickness at x equals 0? 0. Okay, gets bigger as you move downstream. Okay. Let's go back to the problem. First one is the boundary layer thickness decreases as the viscosity decreases. Well, if I look at this equation, now since nu is the same as the viscosity, basically, that part A is obviously true. Right now, but let's check B, C, and D just for the heck of it. A has to be true, right? If this goes down, then that's got to go down. Assuming that the other things are constant, of course. Right. Let's go to B. The boundary layer thickness decreases as the flow speed decreases. If the flow speed decreases, the boundary layer thickness has to get bigger. So that can't be true. B is obviously false. C, the boundary layer thickness decreases as the Reynolds number decreases. Well, here's the Reynolds number here. If this Reynolds number decreases, the boundary layer is going to get bigger, not smaller. So that can't be true. C is obviously false. What about D? Boundary layer thickness grows more rapidly compared to a turbulent one. What's the answer to that? That's false, because we know that turbulent boundary layers grow significantly faster than laminar ones, right? We know that for a laminar boundary layer, delta goes like the square root of x. How do I know that? Well, that's what we talked about in class, square root of x. Whereas in a turbulent boundary layer, delta lam, delta term, what's the answer? How does the turbulent boundary layer thickness grow with x approximately? Is it x squared, x cubed, x to the 17th power, x to the 33rd power, x to the minus 1/5? What is it? Approximately. X to the first power. Right? So therefore, obviously, the laminar boundary layer goes much more slowly, right? Okay. Number 10, we're done with that one. Any questions about that? That was kind of a tricky one, actually. Number 10. Let's see. Stream function. Okay, let's do that one. So this is really the way to do these problems. The stream function psi, there it is, there's the stream function for a 2D, it has to be 2D, irrotational. What mathematical equation am I going to write down for irrotational? Vorticity is 0, which is the curl of the velocity. What else? Incompressible. Well, that's divergence v 0, right? So we've got all those things. We've got a psi. It's 2D. No vorticity. Divergence v is 0. Okay, the stream function. Okay, the first choice is psi equals 0. That's very interesting. We're going to talk about that. Do all these conditions imply that psi is 0? Of course not. I mean, that's sort of meaningless. But before we go on, what exactly does this equation mean? If psi does equal to 0, what does that signify? What can we do with that? If somebody said, aha, psi is 0.
dx is 0.
Now, remember what I said a long time ago? If you assign a constant to a stream function, you get a streamline. Therefore, this is you can get a line from this equation, right? Because psi would be a function of x and y, and that would be 0. So you could get y as a function of x implied. So psi equals 0 represents a streamline of this flow, some streamline. Okay, so A is obviously wrong. B, psi equals 1. Obviously wrong. That just there's no psi can be anything, right? Next one, del squared psi. Oh, that's interesting. Del squared psi equals 0. Well, let's leave that one for now. Let's go to D. Del squared psi equals 1, and then E is none of these. Okay, so we know it's got to be either C, D, or E. Obviously, it's not E. So which one is it? C, definitely. Yeah, C, definitely. Because we have no vorticity, and we've got that. And it's 2D, and we have a stream function. So there's no question whatsoever. It's got to be del squared psi 0. Right? Because we got the two big conditions, this one and this one. And that one. That one, that one, and that one, definitely we've got the Laplace's equation. Oh, by the way, what is the equation for phi in this flow? Yes. We also have del squared phi is 0 too. That's true. Okay, that's pretty much the. Yeah.
I was going to ask a question. Is this still last week's training?
Probably, yeah. I might have one next week. I'm not sure.
Okay.
Probably. Okay. I was thinking of giving another multiple choice quiz, but I don't know. Not sure about that. So, I'll let you know. Okay, if there's no more questions about that, what time do we have? Yeah, we have some time. So let's do. What I thought we would do now is to go over the quiz. Take home quiz, yes. Talk about that for a while. Okay, let's this stuff. Okay. Sure.
Yeah.
Okay. So let's see. This is a problem with a tornado. Let's draw a picture. So what the problem says is that, and this is, I think in my afternoon class we actually got the real data from a real tornado. Actually, I don't know. There was a tornado in Manchester, North Dakota. I think it was in 2003. And you can look that up on the internet. I think people, my afternoon class saw this, right? So there was this tornado, and it was, believe it or not, it was F4. Do people know what the tornado scale is? That's kind of fun. Is Fujita, I think it's the Fujita scale. 0, 1, 2, 3, 4, 5. So 0 is, well, 0 is still pretty bad. It might knock off a shingle or something. I think I don't know exactly what the wind speeds are. You can look them up. Maybe like 60 miles an hour for this one. And then you're getting up to maybe 100 mph at max here for Category 1 tornado. That's actually quite serious, believe it or not. I mean, when I was living in Texas not too long ago, I lived about less than a mile away from a very strong F1, believe it or not. And I wasn't there at the time, but I saw something going on in my office window, some weird stuff going on there. People were warning signs and things. And when I got home, I said, "Well, where's the tornado?" There was no damage whatsoever. I just walked about half a mile away into this community, and there was serious damage. And it was an F1. It was on the upper end of the F1 scale. Some houses were very severely damaged, and you could literally see that I literally walked into the community. It was very serious damage. They had cop cars everywhere blocking traffic, and I literally walked the entire distance of the path of the tornado. Crossed the road, did a lot of damage. So F1 is not a trivial thing. That could be very bad. Like knock off a roof or something. Then of course you can imagine, I don't know what the velocities are, you can look them up. You happen to have an internet connection where you can look up the wind speeds here. I'm just kind of curious to know. I don't know exactly what they are, but I do know this one is about 300 mph.
So you wanted the speeds of which one? Speed 2?
Yeah. Do you have the typical speeds of these? There's ranges, of course.
Okay, so F0 is 40 to 72 miles per hour.
What do you say? 40 to
72 miles per hour.
40 to 72.
F1 is 73 to the 1 to 12.
Yeah, right. That sounds right.
F2 is 1 to 13 to 1 to 57.
What did you say again? 112 to
113 to 157.
157. 4.
So you got 4. 158 to 206.
Wow, 206 is getting up there. Okay, 5.
207 to 260.
260.
And 261 to 318 for F5.
Oh, this is.
Yeah, you skipped 2.
I skipped 2. Oh.
Uh-oh.
2, 3. Wow, so I got the highest one. F5 is what again? 261 to 318. So
The names they have for these are amazing. Like an F3 is severe, F2 is significant, F5 is incredible, and F6 is inconceivable.
there's no such F6.
It's called an inconceivable tornado.
Inconceivable tornado, right? So I can tell you from personal experience that if you are around that range, that's bad. Actually, it's quite very bad. So you can imagine if this is really bad, this is going to knock off your roof or do serious damage to your house. You can imagine what that's going to do. It's going to wipe out everything. It'll literally, this will apparently literally destroy or damage concrete reinforced structures. That's how dangerous it is. So anyway, I'm getting off the subject. We are talking here about an F4? No, F3, sorry. The problem is talking about an F3. But in Manchester, they had an F4. And the interesting thing about this situation is that some crazy person or persons apparently threw pressure sensors into the tornado. That's what they said. I don't know how they ever did that, or crazy, but they did it. And they literally got they literally got the pressure inside the tornado. You can look it up online if you want, but we'll come back to that later. Let's do the problem. So it turns out that the answer that most people got in this problem is quite realistic, actually, very close to the correct answer. The measured answer was something like this. The pressure signal looked like, well, I'm obviously exaggerating, but if you look online, you'll see that this is pressure, and this is time over here. The pressure difference between P infinity, which is here, and the inside of the tornado, which is here at the center, was about 100 millibars, which is 10⁴ pascals. That was literally the pressure difference. And I think the correct answer to this problem was something like, not the exact answer, I think delta P that you got for an F3 was around, I think it was around 5,000, right? So I don't know the exact number, but it was around 5,000. 45. Yeah, right. So this is actually very, very good. You also have to realize that it doesn't sound so good, but it's actually quite good because, remember, the pressure drops as the square of the velocity. So small increase in velocity is going to change the pressure a lot. So it's not linear. Right. Anyway, okay, let's do the problem. So this model for a tornado is actually pretty darn good, which is very good news because that means that you don't need to solve the Navier-Stokes equations, right? You can do it without it. Well, not quite, but almost. Okay, so let's do the problem.
Wait,
So,
didn't you use the Navier-Stokes? You just canceled out?
yeah, but what I mean is
Oh, you can use
putting it on a supercomputer and solving the entire thing with turbulence and right. I mean, understanding how a tornado was created, that requires massive supercomputing, right? But once you've got a tornado, this model is pretty good. Now, of course, we made a lot of arbitrary decisions here. We talked about the tornado was 100 meters, but I didn't really know what it was. I'm just taking a typical number. I don't even know, in this tornado, I don't know what the diameter was. I mean, obviously the diameter changes, so I don't really know. But I don't know, 100 meters sounds too big to me. I mean, that's the size of a football field. That's really, really large. So I don't know if it was 100 yards, but anyway. Okay. So let's do the problem. So the model we're using is this. We have the core of the tornado, which we are going to model as a solid body rotation, SBR. And then way out here, we're saying potential vortex out there. So the first part of the problem was, oh yeah, of course you know that the velocity potential for potential vortex is A times theta, and the psi for a solid body rotation is B times R squared. So that would be for a potential vortex, and this would be for a solid body rotation. Okay, so you've got those equations. So, first part of the problem is calculate the velocities. And the answers are, let's do part A over there somewhere. Okay, so we can calculate V sub R. V sub R is for the potential vortex, is dphi dr. Now, if you don't remember that, that's okay, you'll be on the test, so don't worry. Phi dr is what? 0. And V sub theta is 1 over R d theta. Let's see, what is that? That's going to be A over R, right? A over R. And for the that would be for the potential vortex. By the way, We also have a stream function for the potential vortex too, right? But what about for the solid body rotation flow, VR? Now, for the potential vortex flow, for the solid body rotation flow, there is no velocity potential. Right, but we do have a psi, fortunately. So VR is 1 over r, d psi d theta, and that is 0, right? Because psi depends only on r, and d theta is minus psi r, which is minus 2br. Minus 2br. Okay, so now we can plot these things. Now we got them. Now we can plot them. Let's go to the potential vortex. We see that for the potential vortex, there's no v theta, no VR at all, right? We just have a v theta, and it decays like 1 over r, right? So obviously, it's something over there. It's something at the edge of the core, right? At the edge of the core, we know it's something, whatever it is, right? Actually, we know what it is, right? What is it? It's going to be v sub theta is going to be a over capital R, right? Yes.
For the in part A, you had VR is equal to 1 over R. Why did those switch?
Oh, you mean, what do you
See
mean by
how the
switching?
VR? Yeah. Why
Oh.
does 1 over R for v theta there, but in the v theta there it doesn't?
Oh, well, the reason is because for a solid body rotation flow, we do not have a phi. So we have to use the equations for psi, which are not the same as these equations.
Okay.
See what I'm saying? There's two sets of equations.
There's two sets of equations.
Right, there's one, if you have a phi or a psi, there are equations to get the velocities from them, right? But in this case, we don't have a phi. By the way, why don't we have a phi?
Because it's... Oh, why we don't have a phi in...
Yeah, why don't we have a phi for the solid body rotation?
Because these potential vortex?
No, because the solid body rotation flow has vorticity. We can't have a velocity potential. Right? Okay, right? Okay. So right at the outer edge of this thing, we have a d theta of a over r, right? And then it decays to 0 way out there, right? Because it's right as r goes to infinity, the thing goes to 0, right? Okay, and way out here, I can't reach. I'm not tall enough, but we have P infinity there, right? The pressure is not infinite out there, right, Mike?
Yeah, that was yeah.
It's not infinite. It's just P sub infinity. And we don't really care what it is. It's something. So, all right. Okay. That's just a joke that Mike and I have worked out together. Okay. Okay. So, what's going on inside the solid body rotation flow? And by the way, just to remind you, on a test, you should draw these kinds of pictures. What I'm finding is some students are drawing pictures, which is good, but you should sit there and draw some pictures of the thing before you start writing down equations. That way you actually understand what you're doing, right? Okay, what does the velocity profile look like in the solid body rotation flow? Yeah, we know exactly what it looks like. It's linear with r, right? It goes linear with r. The minus sign doesn't really mean anything because we don't know what b is. We don't care. The only thing we know is it's definitely 0 there, and it has to increase linearly, right? Like that. So it's going to go that way, and then over here, it's going to go that way, right? Just like a spinning disk, right? Well, here's a good question. I'm sure you thought about it. Why is the velocity 0 in the middle?
R is
Yeah, well, yes, exactly, because R is 0. Why? That doesn't make any sense. I mean, a tornado doesn't have a velocity of 0 in the center. So what are we really doing? What kind of model are we using here? What we're really doing is we're using a model that's moving with the tornado, right? We're in a reference frame moving at a constant speed relative to the tornado. A tornado is going to be moving at 20, 30, 40 miles an hour, right? Maybe faster than that. They can move quite fast, right? So that's really what we're doing. We're moving with the tornado, right? Tornado's over here spinning around, and it has a rotational velocity, but it also has a translational velocity, right? And we are literally in the reference frame moving with the tornado, assuming it's moving at a constant speed.
so we neglect the translation.
Well, we're not neglecting it. We're just doing a model in the frame at which we're moving at constant speed.
Oh, our
Remember from physics, if you're moving at a constant speed, all the equations are invariant, right? We're not accelerating. We're assuming the tornado is moving at a constant speed or moving along with it. So we can use the standard equations of fluid mechanics in that reference frame. Okay, so now we really know what's going on. We have a pretty good idea what's going on here. So let's go. That was part A. What about part B? Part B was calculate A and B. What are they? Tell me how to do that. Since you guys already did it, how are we going to do it?
So the velocity, the resultant velocity is given, right? It's 70.
Yes, the velocity at the outer edge of the core is given. This vector is what, 70 meters a second, right? So
Simple algebra just set everything. Set
Right.
everything equal to
okay, that's correct. But what physical assumption are we making in order to get this? There's a very, very important physical assumption we're making in order to do what you're saying. What you're saying is correct, but how are we reaching this conclusion?
Velocity and size is the same.
What you guys are saying is, let's repeat. What you guys are saying, let's write it down. What you guys are saying is A over capital R, which is the velocity at R, right, is equal to 70. And you're also saying that minus 2b times R is also equal to 70, correct? So you can calculate A and B. But why should these two things be the same? You're correct that you should set them equal to both equal to 7. What's the fifth? Yes.
You're saying that the velocity doesn't change because we've changed areas that we're analyzing to exact that location R, so it has to be the same.
Right. Well, yes, but I'm looking for something a little more subtle than that. We're making a big physical assumption that the velocity is continuous as we go across the layer, right? By the way, this model couldn't possibly be totally correct because although the velocity is continuous, the first derivative of the velocity is not continuous, right? So we're obviously, it couldn't possibly look like that and then go like that, right? It's got to be a smooth transition, which we're not accounting for. We'd have to introduce viscosity into there to kind of get this smooth out, right? Well, what if the velocity were not continuous? What happens if it were 60 over there and 70 over there? Well, that can't happen. But why can't it happen? Why can't it be 60 here and 70 there? Why? 60 here and then 1 millimeter above 70. Why is that impossible?
That will also mean pressure is not.
Yeah, everything is discontinuous, but why can't you have that? It's a big assumption you're making here. Get the answer. Well, the answer is viscosity does not allow that to happen. It does not allow a discontinuity. It's always going to smooth out these giant changes, right? You're never going to. You might see it for one microsecond, 1 nanosecond, but then molecular transport will take over and smooth it out. Okay, so you can all calculate A and B. I'm not even going to tell you what it is. It's something, right? So we got A and B. That's easy because we know R. R is 100 meters, right? Well, let's calculate just for fun. What is A? A is going to be, what, 7,000?
Yeah.
7,000. And B is going to be, what is that? Minus 70 over 2 times 100? Is that right? What is that? Somebody calculate that for me.
Negative 0.35.
Negative 0.35?
Yeah.
Okay. What are the units?
Second inverse for B. And
Second, you say second inverse for B?
yeah,
And what are the units for A?
A is like a meter square first.
Meters, you say meters squared per second?
Yes.
How do you know that? Well, let's see. We go back to this equation. We have a velocity on this side, and we're going to get a velocity on that side. Let's see. Meters squared per second, that works. Because then you get the R canceling out, and you get meters per second. That's good. You're right. Meters squared per second is correct. Let's look at B. B inverse seconds must be correct. Because we've got a meter here. Okay, so let's write that down. Can we write that down somewhere? Let's see, over here. A equals 7 times 10 to the third meters squared per second. And B equals negative 0.35 inverse seconds. Okay, so that's good. Let's go to part C. Let's see, what is part C? Part C was calculate, yes. Okay. Now we're getting into the tricky parts of the problem. Very tricky. Especially part D, very tricky. As we discussed with some people. Not obvious what's going on here. But anyway, part C shouldn't be that tough. In part C, we want to know, let's call this pressure P sub, I don't know, yeah, P sub 100 or something. I guess that's good, P sub 100. We'll call the pressure at the center P sub center, I guess, P sub C, right there, I guess. I don't know. Something like that. Okay. What we want to know is what is the pressure difference between P infinity and P zero? Why don't we just write that down? P infinity minus P at 100 equals something. That's what we want to know. By the way, before you even try to solve the problem, what is this number? Is it going to be positive or negative or zero? Positive. Why do you say it's positive?
Because the pressure at infinity is greater.
You're just repeating it. I don't know why. You're not telling me why.
You can draw the free body diagram.
Free body diagram, yes.
And then, because of the centripetal force.
Correct. So what Parshva is saying is, if this is a fluid particle way out there, then what is the acceleration vector for that particle?
It's towards the center.
Yeah, let's draw it over here, actually. Better. Here's the same particle. We'll call it particle A. Here's particle A. What is the acceleration vector? It's going downward towards the center, correct? There's the vector, A. It is a vector. It is a radially oriented vector, right? We could write it minus A r hat, but don't worry about that. Okay. So, if I had a particle that was accelerating this way, but that can't possibly be true. What about the forces on this thing? What forces does the particle have on it?
Pressure forces.
Yes, it can only have pressure forces. There are no other forces that cannot have shear. It's impossible because it's a potential vortex. It's a perfect fluid. It can only have pressure forces, right? So we have a pressure force here, P1, and another one going up, P2, right? So therefore, P1 must be bigger than P2 because that would give us a net force acting on the particle which would be parallel to the acceleration vector, which is correct, right? F equals ma. If the acceleration vector is pointing down, and the net force has to be pointing down, right? In order to get a net force on the particle pointing down, P1 must be bigger than P2. So, therefore, we know P infinity must be bigger than P sub 100. But we know that's true for every storm, right? Because when you turn on the television, they tell you a low pressure center is approaching. What does that mean? That means you've got a storm. And the reason it's a low pressure is, well, that's the reason why it's a low pressure center. Okay, let's calculate it. How are we going to calculate this thing? You tell me. Bernoulli's equation. Did you say Bernoulli's equation?
Bernoulli or Nagel in this case.
Okay, Nager's right. But let's use Bernoulli's equation. It's easier.
Yeah.
So we are going to use Bernoulli's equation, but why is it that we can use Bernoulli's equation? You just say use Bernoulli's equation. Why? Are we allowed to use Bernoulli's equation?
Because of the vorticity being 0, it's easier. Same constant.
Yes, but it's also because it's
yeah, perfect.
it's perfect fluid, right? Okay. So let's use Bernoulli's equation. So we're going to start out there. P sub infinity divided by the density plus the velocity. Well, there's only one velocity component. I don't want to get too fancy here. We'll just say v infinity squared, which is the magnitude of the velocity at infinity, squared over 2, must equal something. What is the something? Tell me what the something is.
If they're the same, then it's going to be the pressure at the 100.
Right. Well, right.
And then,
It's going to be C Bernoulli, correct?
oh yeah, but like that's also equal to
Right. Which is one number, and you're right. It has to equal P at 100 divided by the density plus the magnitude of the velocity at 100 squared over 2.
You said that we jumped. Like I know you're supposed to use Bernoulli, I just jumped to it. But okay, so you say you can't use it because it's a perfect fluid, but is that always number one? Is that always the case? And the other reason was 'cause-
Well, no. Remember the flow chart that we just wrote down a couple of.
yeah. Right. Okay.
Mu is 0 basically. Therefore, and it has no vorticity. Therefore, it's valid. It's valid between any 2 points in the flow.
Right. Okay.
Here's one and here's another. We don't have to worry about the streamlines in this case because there's no vorticity.
So it's
right?
always good to use Bernoulli's with if you see a potential vortex.
If you see any potential flow, it doesn't matter what it is, any potential flow,
You just jump to Bernoulli's. That's
you
great.
can jump immediately to Bernoulli's. That's correct. Any
Yeah.
potential flow.
Is there ever?
But you have to make sure it's a potential flow. If it's not a potential flow, you can't use it. Okay. So, let's proceed here. What is V infinity? 0. Why is it 0?
When you
Yes. 0. What is V at 100? We know that. At 70, right?
So we have on an exam, would we have to prove that V infinity is 0? Because the way to prove is to solve, right? And then you have
No,
to
just well, you got it right there. All you have to do is say
Say
when R goes to infinity, V is 0. It's all right. Okay, so let's go ahead and solve it. P at infinity minus P at 100 divided by the density is equal to V at 100 squared, squared over 2. Let's multiply by density. Okay, can somebody calculate this number? So it's going to be 1, because that's the density of air, times 70 squared, right?
Yeah, very smart by 2.
Okay,
So that's 2450.
2450. 2450 pascals, correct? Let's write that down. Where's all this stuff? Here. Okay, so you get P at infinity minus P at 100 is equal to 2450, right? Pascals. Okay. That was pretty easy. So now the last part, which is worth a lot of points because it's the hardest part for a lot of reasons. Okay. So we're almost there. We're not there yet. We want to calculate P sub 100 minus P sub C. That's what we want, right? Which one is going to be bigger? Is this pressure going to be bigger than that one, or the other way around? Or are they going to be equal to each other? Which is it? P100 really bigger than PC. Why?
We use the same.
Exactly. For the same reason that P infinity is bigger than P1 and P100. Particles are going around in a circle, therefore that has to be true. Okay. How are we going to do it? We're going to use Bernoulli's equation?
We can, but we don't.
Okay, now it gets tricky. Now it gets really tricky. Okay, let's go back again. What did we say? Mu is 0 or mu is not 0, right? Well, which case do we have here? That's a very serious problem. Do we have a case where viscous forces are negligible, or do we have a case where it's not a potential flow? But that doesn't necessarily mean we cannot use Bernoulli, right? So we have to be careful. In order for us to use Bernoulli, we have to have negligible viscous effects, right? Do we have negligible viscous effects in the solid body rotation flow?
Afterwards.
Well, it's a yes or no answer.
Yes. Yes.
The answer is yes. Harshman is correct again. Of course, he knows the answer, so I told him the answer a long time ago. Okay, yes. There are negligible viscous effects in a solid body rotation flow, even though in order to get solid body rotation, you need viscosity, right? You're going to need viscosity to get the whole thing moving in solid body rotation. But once it's in solid body rotation, the viscous stresses are 0. You can find that out just by looking at the Navier-Stokes equations, right? So the answer is, this is true. Okay, now we have two possibilities. Either the vorticity is not 0, or the vorticity, here's vorticity equal to 0, here's vorticity not equal to 0. Which path are we going down? This one, right? Because we have vorticity. Therefore, we can use the Bernoulli equation in this flow, but only on streamlines, right? So what does that mean? That means that I can write, here's a streamline. I can write the Bernoulli equation between this point and that point. That's useless for our problem, right? What I want to know is, I want to write the Bernoulli equation between this point, which is on that streamline, and this, and let's say that point, which is on a totally different streamline, right? So therefore, the answer is, I can use Bernoulli's equation, but if I use it incorrectly, we're going to do that actually if we have time. We'll use it incorrectly, and you're going to get the wrong answer. I'll show you. Okay, so therefore, we can use Bernoulli's equation, but it's useless. So then what do?
We use the other.
We use the other one. Use the other one. What is the
Father
other one?
Navier-Stokes.
Yes. So we're reduced to using a Navier-Stokes equations, right? But are there some restrictions on the use of the Navier-Stokes equations? Really? No, you can use them in any case. You can use them for a potential flow. It doesn't matter, right? Okay, so we therefore are kind of reduced to using Navier-Stokes for this flow. Let's go ahead and use Navier-Stokes. And we have 3 Navier-Stokes equations for this flow. One for the R direction, one for the theta direction, and one for the z direction, right? Which one of those three are we going to use? On your test, you will have it written out for you, polar coordinates. Which one of those three are you going to use in this problem? Are you going to use the r, theta, or the
Theta. You're gonna use theta.
theta equation
Wait, for this problem?
for this problem?
Yeah, it doesn't. We don't have a VR component.
We're trying to find pressure, because pressure doesn't change in terms of theta.
Yeah,
I'm
you
very
want
confused.
pressure gradient in terms
So
of
we
R.
have an r direction equation, like for example x, we'll just call it r. That's one of the coordinates. We have a theta direction, and we have a z direction coming out of the blackboard, right?
We don't need to worry about z.
Correct.
But
So which one of those two are you going to use?
I mean, for both, you have a v theta. You cancel out v alpha.
That's true.
So
So you're saying we should use the theta direction equation?
I mean, that's the only thing, right?
You have to commit yourself. Is that what you're saying or not? I'm only kidding.
Yeah.
Yeah. Okay. He says.
Yeah, put the money down.
He's not. He's putting his,
Yeah.
he's making his bets.
Yeah.
And obviously, there are some people who differ with you.
I agree with that.
You agree with him? Okay, we got two guys.
I
You disagree.
Alright, I hate you.
You disagree. Okay, why do you disagree? Tell me.
Because we want pressure gradients like P, partial of P with respect to R. That's what we want.
Yes. Yep. Parshman's got it.
But you want the partial.
Right. In this equation right here, you're going to get the theta derivative of the pressure. Right? Well, we don't care about the theta. The theta derivative of the pressure is 0, by the way. There is no variation of the pressure around a streamline in this case. Therefore, this is useless. It's not going to give you anything. We want the r direction equation.
So that's just a wrong assumption to assume that just because you don't have a VR.
That is correct. So let's go ahead and write it down. Now, if you go to the book or go to online or go anywhere you want, and you write this gigantic, it's very, very large, and it goes on, right?
That's not.
You will find that it reduces, in this case, you know it's absolutely true, I'm not telling you a lie here. It reduces exactly to this. Let's write it down. Where am I going to write it? Somewhere. I don't have any. Where's my, oh, there. Okay, so we want the r direction. And we have the case where VR is 0, right? And in fact, v theta depends only on r, right? So this is a huge simplification. V theta depends only on r, and VR is 0. And everything in the equation wipes out entirely, except for, let's write it down, equals, on the right-hand side, minus the partial of p with respect to r. That shows up. But that should not be surprising. Look, right? The pressure depends on r. It's the only term that shows up, right? Now, what does this term represent, by the way? Give me a real solid physical words that tell me what does minus PVR mean physically.
The change in pressure along the radius of the.
Right. What I was really looking for was the net pressure force acting on the fluid particle. Net, N-E-T, net. National Educational Television. That's, I don't know. Net, N-E-T, the net pressure force acting on the particle, right? And now, all the viscous terms are 0, plus 0. They are going to be nothing. What shows up on this side? Well, lots of things show up, but they all go to 0. And if you look at the equation carefully, there's only one term that shows up. Minus the density times v theta squared over little r, the coordinate. Right? I'm sure that's what most of you probably saw. Right? What does this term represent?
So it's like the centripetal force, at least for
Yes, it is the centripetal acceleration. Not really a force. So this is This is the acceleration, and it is being equated to the net forces on the object. That's exactly what we said right here, right? The pressure difference is balanced, has to equal the inertial force. And where does mass come in? Well, it comes in from the density, right? There's mass there. The inertial is right there. Okay, but there are two negative signs here. So we can cancel those out. So we get that. So let's see, what is this equation telling us before we solve it? What is it telling us? It's telling us that the radial pressure gradient is positive. Because density is positive, anything squared is positive, and that's positive. Positive. R can never be negative. It's impossible. Therefore, according to this equation, the PDR in the solid body rotation flow is greater than 0. What does that mean? That means that as we move in the positive R direction, the pressure must increase, right? That's exactly what we said. Okay, so now we've got that. Let's go ahead and solve it. How are we going to solve this? P100 minus PC is what we want. Let's get rid of this, get rid of that. Let's see. Can we integrate this thing? Well, yes, we could. That's the only possibility, right? There's no other possibility. But we know what peak theta is. Where is it? Here it is. This is the guy we want, right? By the way, we're going to do the problem the wrong way in a minute. You'll see we're going to get the right answer. No, we're going to do it the wrong way. You're going to get the wrong answer. But okay, well now we're going to do it the correct way. This is the one we want. We don't want that. This is the flow we're talking about, right? So it's minus 2br. So we get, let's plug that in, rho. I'm going to square minus 2br right here. I'll get 4b squared, r squared, divided by r, right? R is a coordinate. It is not the radius of the circle, right? It's a coordinate variable. And that equals 4b squared rho times r, right? And that equals PdR, which is just a regular derivative. That's what it is. So now we've got to integrate that. And if we integrate that, let's integrate on both sides. 0 to capital R, right? We're going from R equals 0 to R equals capital R. 0 to capital R. Let's go ahead and do that. So this guy is going to be P at R, which is P at 100, minus P at 0, which is P sub C. And that equals 4. B squared times the density times, well, this is usually R squared over 2, so I'll put in R squared over 2. Okay, so somebody needs to calculate this for me. What are we going to get? Let's write here 4 times B, which is B squared, 0.35 squared, times density, which is 1, times 100 meters squared over 2. Did I get that right? 4 times 0.35 squared times 1 times 100 squared over 2. Did you calculate that? Somebody calculate that for me. I think I can do it. No, I can't do it. I can estimate it, but I can't do it. I think we're going to wind up getting this, by the way, but we'll see. It's positive. That's good.
It ends up being 2450.
It does? You're sure about that?
Yeah, 2004.
Same thing. Okay. Turns out to be the same thing. That's interesting. Okay. So the answer is, let's write that down somewhere. Yes, this turns out to be 2450 pascals. Therefore, what is P infinity minus PC. What is it equal to? It's equal to twice.
Yes.
What is that exactly? 0, 0, not 29.
40.
Oh, sorry, 4,900. I can't even multiply. Okay, it's getting too late for me. I can't multiply anymore. Maybe I should retire because I can't multiply. Once I can't multiply, I will retire. I can still do it.
Still got time.
I need a calculator.
Still the glory days,
Otherwise,
Professor.
I can do things on MATLAB because I can't do them in my head anymore. Anyway, so the answer is 4,900 pascals. What would happen if we increase the velocity to an F4? Well, let's see. I think the pressure is going to be much lower because of this. You might want to calculate it. I'm curious to know what it is. Maybe we can estimate it somehow. We should be able to estimate it, right? Because of this, right?
The B will change. Right?
Yeah, because the velocity is going to go way up. It's not going to be 70 anymore. It'll be maybe 100, right? Let's say 100. So for the heck of it, let's instead of putting 70 in here,
Even the radius will change.
well, we'll keep the radius the same. Oh, we didn't put,
The B is like negative 0.35.
right, What? right, I guess you're right. So I guess it's the R. I'm not quite sure how it's going to work out, but I can't quite see it off the top of my head. But isn't this going to be, well, it's going to be, I think it's going to go up from 70 to, let's say, 100 meters a second. So it's probably going to increase like 100 over 70 squared. What is 100 over 70 squared? Just guessing. Can somebody calculate 100 over 70 squared? I'm just guessing off the top of my head. 100 over 70 squared. What is that?
It is 2 times.
2?
Yeah.
Really?
2.04.
2? Wow, it's around 2. Wow. Oh, that's amazing.
Yeah,
Because-
you get around 10,000.
Because that's going to
9,000.
That's going to double this, which is very, very close to the measurement. The measurement was 1,000. Ours was 10,000.
Yeah, it was 10,000.
Yeah, so all you have to do is go from 70 to 100. And anyway, it seems to work out. Maybe it's just by coincidence it works out because we don't know the radius. That's the problem. Okay. Oh, okay. Now we're going to do the problem the wrong way, and we're going to get the wrong answer. Let's do it the incorrect way. Let's do the Bernoulli equation from here to there, right? So we've got P of 100 over the density plus velocity at 100 squared over 2 is P at the center over rho plus the velocity at the center squared over 2, which is 0, right? Okay, let's see. That's very bad because this equation says that the pressure, it's saying that the pressure at 100 is going to be less than the pressure at the center, right?
Yeah.
Right?
Yeah, which is not.
Right. So we get P at 100 minus PC over density is equal to negative V at 100 squared over 2. So what's going to happen if you, I'm not sure what's going to happen, but what's going to happen is, this is obviously wrong. So what you're going to get, you're probably going to get this answer, and then you're going to add it to this other answer, and they're going to probably more or less cancel out, I think. I don't know if they're going to totally cancel. So you're going to wind up with
0.
like nothing, right? Which obviously is wrong, right? And now you can see you cannot use the Bernoulli equation in this case. You can. You can use it from this point to that point. And let's do that. Let's find out what you get. Suppose I'm on one of these circles. Then I would get P at, let's call this point A and point B, P at A over the density plus the velocity at point A squared over 2 is P at P. But you get something which is useful, right? Now, these velocities have to be the same because you're on the same circle, right?
You basically get no.
Yes. So what it's saying is that these circles are streamlines, but they're also constant lines of constant pressure, right? So when you see a storm on a map, and you see these pressure fields that they're showing you, those are probably also very close to being streamlines. Sort of see the constant pressure lines, constant iso surfaces. Okay, I think we killed that problem entirely. Right? So let's see how much more time we have. A few more minutes. I thought we would do maybe one more problem. I'm not sure. Any question? Is there anything in the class that you're having difficulty with? Any concept?
Finding the velocity profile.
Finding the velocity profiles.
For like some flow.
What do you mean? Just any flow at all? You mean by using Navier-Stokes equations or something?
Yeah.
That's a pretty vague question. I mean, I'm not quite sure how I'm supposed to answer that question.
And then, from the velocity profile to calculate the shear stress, there's just one equation.
I see what you're saying. You're saying if I have like maybe a channel flow or something, I've got flow going through the channel like that or something.
Yeah, and I need the shear.
Oh, okay, that's a good question. Let's talk about that. Well, the only other thing I want to talk about today, I don't think we have time, and I would like maybe the next review session we'll do this problem. This problem set right here. It's published online. I would like, this one.
Oh, so we are having a review session? Another one?
Another one, yeah.
Is that like 100% confirmed?
Yeah, more or less. Yeah.
Same room or
Well, I don't know. Well, I'm not sure about the room, but
is it time?
this is actually a really good room. So maybe I should try to reserve this room.
Is the time going to be the same?
Yeah. Anyway, I strongly recommend everyone doing this particular one. There's the one I just put online. And the reason why actually the first one you've already done already, but I really would like everyone to do, especially problem number 3. That's the one I want people to be thinking about. Problem number 3, this blue picture here. Pay very close attention to that problem. We'll do it in the next review session, perhaps. I think I published solutions to this. I'm not sure if I did or not. I will.
Professor, I also had a question about the Reynolds number.
Mm-hmm.
If the Reynolds number is less, then does that mean the flow is laminar?
You
Is
mean-
there some correlation between turbulence and laminar?
Well, yeah. I mean, it depends on the flow, right? Every flow has a critical Reynolds number.
Oh,
Like, for example,
okay.
right, the critical Reynolds number for a flow is going to depend on the geometry. For example, in channel flow, the critical Reynolds number is around 5,000. In pipe flow, the critical Reynolds number is infinity. There is no theoretical. There is no Reynolds number that is known to predict the instability of a pipe flow. In other words, theoretically, a pipe flow can, if you have perfect conditions, like I said in class, you could have laminar flow in a pipe up to extremely high Reynolds numbers. In fact, in that film on turbulence, he briefly talks about that.
So if
But that doesn't mean that you're not going to get turbulence in a pipe. It just means that pipe flow is more stable than channel flow. That's all it means. It doesn't mean that you're never going to get turbulence. It just means that the laminar flow in a pipe is more stable, and there is no known critical Reynolds number. But that's a technicality. The transition point in the pipe flow is going to depend on how strong the disturbance is. In other words, if your laboratory is extremely quiet, you may never see turbulence in a pipe. But if your lab is not quiet and you go into your laboratory and you slam the door shut, the flow might instantaneously turn into turbulence very quickly.
So then it's not stable.
It's not it. Well, right, it's not stable, right? But the thing is, there's no number that says above that number it's not stable. It's a very complicated mathematical problem, and nobody really knows the answer to this problem.
So is it correct to say that if the Reynolds number is decreasing, my turbulence is decreasing?
You mean by decreasing? I'm not sure what you mean by that. You mean as the Reynolds number goes to 0, then the flow can never ever be turbulent at some point.
Oh, so
But
there is
the
not
point-
like a relationship.
Yeah, but what you're saying is there some magic number that below which the flow can never be turbulent? That's what you're saying. And the answer to that question is no, because this so-called magic number that you're talking about depends on the geometry of the flow. There is no magic number. Typically, people say when Reynolds numbers are above 1,000, then you typically see, in the real world, you would see turbulence.
Also,
But it doesn't mean there's some exact number sitting out there, like 79.1. No, there's not. There's no such thing. There is this case right here, where there is a theoretical magic number, but this is very rare. There are other flows where there are these magic numbers, but some flows have them and some flows don't. And the reason for that is no one knows why. That just happens to be the way the equations work out.
Also,
You can
like,
make certain predictions.
there is no way to measure how much turbulence I have, right? It's just
Sure
either
there is.
turbulent or not turbulent. I cannot do
Yes,
this is-
generally speaking, a flow is either turbulent or it's not. There are transitional cases, but generally speaking, in the real world, you're either going to have a laminar flow or you're going to have a turbulent flow.
We cannot be like, this is more turbulent than that.
No. I mean, you can have flows that have stronger turbulent intensity than other flows, but they're still turbulent.
Yes.
Basically, you only have two states. One is laminar and one is turbulent. There's really nothing in between. It's kind of like liquid and ice and liquid, right? You don't. There are no such things as, well, it's somewhere between a solid and a liquid. I mean, it's either going to be solid or it's going to be liquid. It's either going to be a gas or it's going to be a liquid. Same thing with turbulence. You're either going to see a turbulent flow in nature or you're going to see a laminar flow. There are some, as I said, there are some odd cases where the flow is transitioning from one to the other. But generally speaking, that's not what you see in the real world. The weather on the Earth is totally turbulent. I mean, that's a turbulent flow.
Yes.
It's almost never laminar. Whereas flowing your veins and flowing the capillaries in your veins, that's going to be a laminar flow almost always because it's such a tiny Reynolds number. What else? We're going to have another review session, and like I said, the next week we're going to go over dimensional analysis, and I gave you another problem set on that, and that's going to be really important. We're going to go through that next week very, very carefully. There's going to be one problem on the test on dimensional analysis. So if you really understand dimensional analysis really well, which I'm sure you will, it's not that difficult, then you'll be in good shape for that. But you've got to do these two problem sets that I put online. That's very important. I don't know if I put the answers online or not, but anyway, do them. That's the problem to do. Problem number 3. That one.
Are all the problems worth the same? It's like the 40 multiple choice and the rest that we can choose from. Are they each 25 points?
No. The multiple choice section is 40, and the other problems are 20 apiece.
20 pieces, okay.
So you choose 3 of those, you get 60 points, and for the multiple choice, you get 40, and that's 100. So that's about it. That's about it. If you guys have any more questions, I'd be happy to stick around for a little while longer. But
So, yeah, like, while calculating